Hello everybody, welcome to this video on buffer management part 2. So we were discussing about buffer management in the transport layer. So we saw that for every connection, the transport layer has to maintain a set of buffers so that it can use it to store the data which is coming at the sender side, coming from the application layer, and which is to be sent to the network layer. And at the receiver side, the buffers will store the data which is coming in from the network layer and will go to the application layer. So buffers are very important, and we saw different buffer organizations in the previous video. So let us look at one important aspect of buffer management, that is what if there is a mismatch between the data rates between the application layer and the network layer. So we will see at the receiver side first. So at the receiver side, so I have the application layer, I have the transport layer, and I have the network layer. And these are the interfaces. So the transport layer here has some buffers. So at the receiver side, okay, the network layer will bring in the data and write it to the buffer. Okay, and the application layer will read the data from the buffer. So the application layer will read and network layer will write to the buffer. Now this rate at which this read and write is taking place, this may be different. So this may be at a data rate of, say, data rate 1, and the other may be at a different data rate, which may be, let's say this is data rate 2. So the two data rates, data rate 1 and data rate 2, may be different. So one may be fast, one may be slow, whereas and this mismatch in the data rates of reading and writing may cause two issues. First issue is underflow. Underflow will occur when the network layer is writing very slowly, whereas the application is trying to read it very fast. So since the network layer is writing the data into the buffer very slowly, so the application layer will find that the buffer is empty most of the time. But then this does not cause much of a problem because there is no data loss. Of course, it will take more time for the application. The second problem is that of overflow of the buffer. So this will happen if this data rate, that is data rate 2, is very fast, okay, as compared to data rate 1. Okay, so in that case the network layer will keep on writing very fast, and the data application layer is reading the data very slowly. So the network layer may find that all the slots in the buffer are filled up, so it cannot write that segment anywhere. There is no space to write in the buffer. So what will happen? This can lead to loss of data. So the packets will be dropped. Loss of data. Okay, and loss of data, if there is loss of data, then there is definitely a problem. So we have to see if we can find a solution for this. So the solution for finding a or for managing the flow with respect to the buffers at the receiver side, this is known as your dynamic buffer management. Dynamic buffer management. So let's say the sender is here and the receiver is here. The receiver has certain buffer slots. Let's say it has got 5 slots. Out of this, let's say it has got 3 slots already used, and two slots are empty. So what the receiver can do, the receiver can send this buffer information, how many buffers it has free, to the sender. So what it is doing, basically it is advertising the buffer. Advertising the buffer space. Okay, and when the sender finds that the buffer at the receiver is only 2 buffers left, then what it will do, it will adjust its window size. It will adjust its window size. Now this problem does not arise if you have a stop and wait, because you're sending one only at a time, so your buffer size of 1 is good enough. So this whole discussion does not pertain to stop and wait, but for the sliding window protocols, this is how it is going to be managed. So what is this dynamic buffer management? The receiver will, from time to time, it will advertise the buffer space. It will send the buffer space to the sender, and the sender, on receiving this, will adjust its window size to reduce the flow. So that way the buffer will be managed dynamically. So at runtime it is going to be adjusted. So here this is an example. So here I have A is the sender and B is the receiver. Okay, so initially in the first message, A requests for 8 buffer. Okay, now B says that I cannot give you 8 buffer, I can give you only 4 buffers. So it sends a message which has an acknowledgement, some acknowledgement number, some sequence number, and it says buff is equal to 4, means 4 buffers are available. So A, with this information that it has got 4 buffers, it sends the first data. Okay, now A has got 3 buffers left. Then it sends the second data. Then it has got 2 buffers left. Then it sends the third data. It assumes that it has got 1 buffer left. But unfortunately, this message, the third data, gets lost. Okay, now at the receiver side, how many buffers are there? 2 buffers are there. But A thinks that it has got only 1 buffer. So now B here acknowledges that, B sends an acknowledgement that A, it sends an acknowledgement, a cumulative acknowledgement for 0 and 1, and permits 2 and 4, 2 to 4. Buffer 2 to 4, 2, 3 and 4. So it has 3. So it says buffer 3 buffers are left. So A will update its buffer, whatever is the buffer allocation, to 3. Then it sends data M3, M4. Okay, as it is sending, it is decrementing this buffer count. So 2, 1. Okay, then at this point, for segment 2, that segment that got lost, this one, it is retransmitting because of a timeout. Okay, it retransmits. So now it knows that it has got 0 slots left. Okay, so no more slots, no more buffer space left for A. Now everything is acknowledged. So here there is B sends an acknowledgement to 4. So 0 to 4 has been received. Okay, and buffer is 0. It says that it has not yet processed, B has not yet processed the segment, so buffer allocation is 0. Then again after some time, A again sends another advertisement. So it says that it acknowledges 4 and buffer is 1. So now A can send 1. Okay, and then before A can send 1, B again found some more buffer space and says buffer space is 2. So buffer space here would be incremented to 2. So now A has got 2 buffer space, so it sends 2 more data. Okay, so after sending 2 more data, it is 0. So A is blocked again. So A sends a message, acknowledge 6, and buffer size is 0. So if it is 0, A cannot send anymore. Okay, A will have to wait. Okay, now let's say now here after some time B has finished processing everything, all the buffers are free. So here it sends a message. Here this message is important. It sends a buffer update. So it acknowledges 6 and it says buffer is equal to 4. So now buffer is equal to 4. But what happens? This message gets lost. So here B has got 4 buffers for A. A is thinking that it has got 0 buffers, so it is not sending. B has sent an acknowledgement. Now this acknowledgement gets lost. So A still thinks that its buffer is 0, so it waits till it receives an acknowledgement. So this is a situation where you can have a it is a potential for a deadlock. So buffers are available with B, but A is not getting the message. So this has to be, so that's why these acknowledgements with the advertised buffer size has to be sent from time to time by the receiver in order to avoid this kind of a potential deadlock. So you have to ensure, the system has to ensure that the acknowledgements are sent frequently. Why? To avoid potential deadlock. So, as you can see here, so maybe the next message which will come will have ACK is equal to 6 and buff is equal to 4. So maybe this will reach, and A will now update its buffer allocation to 4. It will adjust its sending window size to 4 and then start sending the data. So this is known as this method is your dynamic buffer management in your flow control. So that is all in the flow control and buffer management aspect of transport layer.